Disappointing, I know, right? So today we're going to be looking at limits at infinity. Tomorrow the limits of sequences, reviewing it all, and then reviewing all the sections in chapter 12 on Monday for our test on Tuesday. So here if we take a look at f of x equals x plus 1 over 2x, and we want to find the limits as x approaches infinity. We want to find the limit of f of x as x approaches infinity, and also the limits of f of x as x approaches negative infinity. So just by looking at the graph, as x increases without bounds, as x approaches infinity, what value is it approaching? What about when it's going to negative infinity? What is that dashed line? That's a horizontal asymptote. So you're going to see the relationship as we progress here of our limits at infinity and our horizontal asymptotes, almost one and the same. So when we take a look at limits at infinity, we define it as if r is a positive real number, then we have the limit of 1 over x to the r as x approaches infinity. What do you think this limit is? So as x gets larger and larger and larger, increases without bounds. What's going on with 1 over x to the r? It's getting smaller, 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 pretty much ending up at start with 1 over 1, 1 over 5, 1 over 10, 1 over 100, 1 over 1,000. Smaller, smaller. Looks like it's approaching 0. And x also if x to the r is defined meaning that my x to the r is not 0, can't divide by 0. So when x is less than 0, we're going the other way as far as we have the limit as x approaching negative infinity, 1 over x to the r. What is this limit approaching? 0 again. All right, let's start off with perhaps, 1 over negative 1, 1 over negative 5, 1 over negative 100, 1 over a negative 1,000. That number is getting smaller and smaller and smaller. It is getting closer and closer to, say, 0. So when we're looking at those limits at infinity, it is pretty simple as far as if I have 1 over x to the r, that whole thing just goes to 0. The same thing with our limits at infinity. We have those properties of those limits that we discussed in 12.1, where we had arbitrarily to say that the limit of f of x equals L g of x, limit of g of x equals k at scalar multiplication. Where we had the limit as x approaches c of b times f of x. What was that equal to? What does that scale? What do we do with that b? You just pulled it on out, so we just left with the limit of f of x, which is L. So I'm left with the scalar multiple b times my limit of f of x. And we also had the product, which is just what? The limit of f of x times g of x is the same thing as the limit of f of x times the limit of g of x, which is
on the scalar, the x.
Thank you. I was just think black lines so you really can see it. My pen died out of black ink. So here the sum and difference, the limit as x approaches c. What do we get here? Absolutely. And our quotient gives us and finally the limit as x approaches c of f of x raised to the nth power L to the n. Absolutely. Again, I showed you this guy. You know, we looked at this stuff last week when we went over 12.1 or the week before. I don't know. But the limits of properties. All these properties hold true for my limits at infinity as well. Just because we're using infinity doesn't mean we can't use any of these properties. So when we have the limit of 4 minus 3 over x squared as x approaches infinity, how can I use my properties here? I'm subtracting, right? So I can split this up into two separate limits. What's that first limit? The limit of 4 as x approaches infinity. Why? So what does that look like? 4. F of x equaling 4. Alright? Absolutely. Yeah, it's just a line y equals 4. Is it dependent upon x at all? Yes, no? No. When x is 5, when x is 10, when x is 5 million. Right? I'm still going to have 4. So in this case, the limit of 4 as x approaches infinity is just 4. And what's the second one? I can treat 3 as a scalar multiple, right? 3 times 1 over x squared. I'm just pulling out that scalar multiple. What is the limit of 1 over x squared as x approaches infinity? Absolutely. We just had that right on over here, right? Limit of 1 over x to the r is equal to 0. So we wind up with the limit is equal to 4. Not bad, right? Anything different here? Limit of 7 as x approaches infinity? Minus? So those limits of 1 over x to the r as x approaches infinity, there's nothing to it. It just pretty much disappears. Right? Sometimes, though, it's a little bit more complex rational functions we look at. In that case, we want to go ahead and we divide the numerator and denominator by the highest power term. In the denominator. So you look at your rational function, which in particular in the denominator, find that highest degree associated with whichever term, and that's what we're going to divide each term with. And then we can go ahead and just use our properties of our limits and take the limit of each term. From there we come up with our answer. So here we have the limit of negative x plus 4 divided by 5x squared plus 2 as x approaches infinity. What is the highest term, the highest power term in the denominator? X squared, absolutely. So I'm going to take that x squared and divide each term by that. And that simplifies to what? Negative x over x squared is? It's what? Negative 1 over x. So again, I can use my properties of limits. I have a limit of the quotient, which is the same thing as taking the quotient of the limits. So the limit of my numerator divided by the limit of my denominator, and then I can also take the limit of each term. So here, all we're doing is taking the limit as x approaches infinity of negative 1 over x, 4 over x squared, and so forth. So what is the limit as x approaches infinity of a negative 1 over x? 0. If this is my 1 over x to the r, where r is just what? 1. So I get 0. What about 4 over x squared? X to the r power. Again, here's my r is 2. Almost looks like a robot. Look. There's the eyes, nose, and...
Oh my gosh. I get the first one, then I get 1 over x squared, but I don't understand the 4 over x squared.
Well, think of 4 as your scalar multiple, right? 4 times 1 over x squared. Well, again, 1 over x squared is going to go where? To 0. So 4 times 0. Think of it as any constant over x to the r.
Okay.
Right. So 5 goes where? 5 goes to 5. Johnny 5. And absolutely. And I destroyed the face now, right? So what does this equal? In your notes, I think it says negative x cubed. Seems it's a negative x squared. So here we have the limit of negative x squared plus 4 divided by 5x squared plus 2 as x approaches infinity. What is my largest term?
X squared.
So simplifying, I have what in the numerator?
Negative 1.
I don't have 0.
Oh.
I did not take the limit yet, so I do not have 0, right? So here we have the limit, negative 1 plus 4 over x squared over 5 plus 2 over x squared. So now we can go ahead and evaluate the limit at each term. So in the numerator I have what? Negative 1 is negative 1. 0. So here we come up with that limit equal to a negative 1. What about this one? What is my highest power term in the denominator? X squared. Again, we don't look at the highest power term, the highest power term in the denominator. So in this case, it is x squared. So dividing each term by that x squared. simplifying, we get that limit of a negative x plus 4 over x squared divided by 5 plus 2 over x squared. So what do I get with 4 over x squared?
0.
All right. What do I get with 2 over x squared?
0.
Those were the tough ones. 5?
5.
Another tough one. What about negative x? Sorry? I heard someone. Negative infinity, right? The limit as x approaches infinity of negative x, well, as x gets larger and larger, my negative x says I'm getting smaller and smaller, I'm approaching negative infinity. So I'm winding up with a negative infinity over 5. So what is that limit? Absolutely does not exist. Again, a limit means that my f of x is approaching a unique number, not infinity. Infinity is not a number. Yes.
So like every time you do like marking down or you putting it over, do you have to put the limit like next to it, or can you like start out with it? You know what I'm saying?
You mean skip this part?
Like if you do it the first time, but then you just like kind of like mark through the equation.
So you mean write it this time and then say, okay, this part is doing this and this part's that. As long as you show the work. I always show more work than that's needed, so everybody can understand what I'm doing. So a lot of this work does not need to be shown. But don't forget, folks, even if the answer is as easy as 1 plus 1 is 2, show something. So if you do make a simple mistake, I can give you most of those points. Versus if I just see the answer and the answer is wrong, I can't give you any points. Do you have to show all your work like I'm doing? No. I always show a little bit more. So here are the graphs that we just did, the functions we just did. And I think, again, in your notes, that middle one says x cubed, which should be x squared. So if you take a look at this, what is that dashed line that drew in there? Horizontal asymptote. What was my horizontal asymptote for this one?
0.
For this one? It actually went underneath the x-axis. And that last one? No horizontal asymptote. It does have some sort of asymptote though, right? What is that called? Slant asymptote. So here, and what was the limit of this? First one. Limit of the second one? Limit of the last one? So as we showed in that first, the limit as x approaches infinity or negative infinity is equal to
Horizontal asymptote.
absolutely. It's equal to that horizontal asymptote. If we take a look at the three that we did, here's our first one. First of all, how do I come up with the vertical asymptote? I guess you guys review that for the final then.
That's 0 squared and this one.
Is that what?
So the x is equal to 0.
So the denominator, absolutely. So the denominator equal to 0. That's how we come up with our vertical asymptotes. How do we come up with the horizontal? Start reviewing for the final. Do I say anything equal to 0? Or do I compare something? I compare the powers of my numerator and denominator. So in this particular case, what's the power of my numerator? And my denominator? So my denominator has a greater power, and I came up with an asymptote of y equals 0. Over here, comparing my powers, what do I have? They're equal. So what was the asymptote?
Coefficients.
The ratio of the leading coefficients. This one? Why?
It's the top.
Numerator has a larger power than my denominator. So, if we break all that down, there's our rational function f of x equals n of x over d of x, where n of x is expressed as an nth degree polynomial and d of x as an nth degree polynomial. So we say that the limit of f of x equals 0 as x approaches infinity or negative infinity. In what case? What's the relationship between my n and n? I'm sorry? Absolutely. When the denominator is larger or if n is less than m. Good one.
Thank you.
If I have the ratio of the leading coefficients, absolutely. If n equals m, and does not exist if that's what my numerator. So just like before, when we came up with our horizontal asymptotes, in this case, all we really have to do is look at those powers to come up with the horizontal asymptote, which in turn gives us the limit of that function. All right? So, let's manufacture some greeting cards. That costs 65 cents per card to produce. Initial investment of $4,500. And they give us a cost formula along with the average cost just by dividing by x. And we want to find the average cost. And we produce 5,000, 50,000, 500,000. And then also take the limit as x approaches infinity. So, how do I find this first one? Absolutely. Let's plug it into our formula. Now, there's no calculator sitting at our desk, so what should we do? Okay. What are we going to do then?
Separate.
As Habib said, we can go ahead and separate this into two separate terms. So now when we look at this first term, what can we do? And my second term is just what? 45 over 50. 9/10, so we're just 0.90. Absolutely. Which is? $1.55. You're not being intimidated by problems like this, folks. As you can see, calculators aren't needed for this, right? So, part B, we're using 50,000, so what's going to change? This won't change at all, that first term, right? I'm still going to have that 0.65. In my last term, I get another 0 in my denominator, which is the same thing as doing what? Moving my decimal over 1, absolutely. That's 65 cents plus 9 cents.
Oh, sorry.
No worries. How much? $0.74. And then when we had 500,000 cards produced, what are we going to wind up with? What's that? $0.66. Round accordingly, right? Because this is what? 0.65 what? 9. So So round accordingly, right? So now we're going to get the 66 cents. So the last part of the problem, though, it asks us to find the limit of this cost function, the average cost, as x approaches infinity. What do we get? And why?
Oh,
If you want to do this stuff, go right ahead. But since we know about horizontal asymptotes, sure. Why? What's equal? Let's show said that my n is equal to m, right? I have a first degree polynomial over a first degree polynomial, which we know when that happens, the horizontal asymptote is defined by the ratio of the leading coefficients. So the leading coefficient of my numerator, 0.65, my denominator, 1, which gives us 65 cents. If you wanted to, we could divide everything by x, come up with that exact same answer. Let's try a little bit easier. Questions?